Alright, so good everyone. So today we'll be looking at three-phase diode rectifier. So let's watch out and see how a three-phase diode rectifier works. So you have, in that case now you have that. The first one to phase A, and this to phase B, and this one to phase C. Okay, so now, we have now a three-phase rectifier, but this is, remember, this is three-phase diode rectifier, right? It's a diode rectifier. In other words, it's uncontrolled. Don't control anything, just put it there. Now it's going to the voltage. Okay, what I'm going to get here will be a DC output, right? So we'll have that, right? Now, so in this case I need six diodes with a three-phase source. Alright? So the best way to understand this is to use the principle of our single phase, the one that I did earlier. Alright, please, let's watch out how a three-phase uncontrolled rectifier works. Okay, so did you see that? We have that 6 pulses out. Alright, so now, so if this is your VO, the output voltage, by the time you take the output voltage and divide by the resistance, right, you get your output current, which will still look the same way, like that. Alright? Okay? And then, now let's now look at how this current here will look like. Now we've seen how the current here will look like, which is our DC, but here is our AC that is going in and coming back, going in and coming back. As the thing is going in, if it gets in here, this diode and this diode will conduct, right? We have 1 and 6. Okay, so you're going to have this. So the AC that gets in here, the AC that gets in there will now look like that. On the negative half cycle, right, on the negative half cycle, which we're going to now use this diode D4 with these two D3. Okay, now we're going to have the negative half cycle, okay, with 3, 4 and that. All right, so you have this. Can you see now, instead of having a pure sine wave this side, now look at how it looks like. That means that this inverter, this rectifier is now injecting harmonics, because this contains harmonics. Inject harmonics to the grid. Okay, so now if you want to now get the current through the diode D1, let's look at just D1 first. You can see at this point for our diode ID, just ID1, you can see this is where we have 1 and 6 conducting, and this is 1 and 2 conducting. So that means this diode only conducted at this region. Alright, so you have that ID only conducted at that region. And that's all. After that, it's now 0, nothing. It's not conducting here. Alright. So the next step, it will start again somewhere. Sorry. We start again like that, okay, to conduct. Yeah, so the whole of this region, this conducts only at this point in time. So this is your ID1. Okay? Alright. Okay, so now let's now look at what is the value of this. Let's see what is the peak value of that. Alright, remember that now with here, if you check here between voltage across between A and B, that is your VAB, okay, which is your line voltage, right? Your line voltage, isn't it? So if this is the voltage VAB, right? the peak value of this voltage, all right, across A and B will be the same as the peak value of this DC output. And then what is the peak value of this? All right, now we said Vrms is saying V peak over root 2, isn't it? Right? So that V peak is root 2 V RMS. Now, but this VRMS is your VLL, right? It's your line voltage. So that means here we can write that as root 2 by VLL, all right? So this peak value here is root 2 VLL. Okay? So that the peak value here for the current, IO, will be root 2 VLL divided by the load, the resistance. Did you get that? Alright? So even the peak value of this IA, the peak value of this IA will also be the same thing as root 2 VLL over R. That's the peak value of this IA. Okay? And then here also, right? Root 2 VLL over R, the peak value of that. Okay, so now another thing again is, let's see what is the timing, the different, the time between this point and that point. Remember, now the whole of this from here to here, we derived it just for one full cycle, like that, all right? Okay, like that, which is your 2 pi. So from here to here is 2 pi, right? So now how many pulses we have? 1, 2, 3, 4, 5, 6. 6 pulses. Now 2 pi divided by 6 will give you pi over 3. So it means that from here to here is pi over 3. So, okay, so we are going to use this to derive the RMS value and the DC value of this signal. Okay, so watch out for the next video. Okay, thank you.